In this activity, we're going to study ratios of frequencies. Here is a device that I built. It's got 3 strings on it. There are 3 guitar machine head tuners attached to 3 E strings for a guitar. These are steel strings, and they're all tuned to the same frequency right now, pretty much. And what we're going to do is we're going to vary the lengths of them by using little frets that I can put under the strings in order to change the frequency. When you change the length of the string, as shown here, you get a different sound. Of course, the shorter the string is, the higher the frequency will be. The tuners are designed so that they can hold the tension to a fixed value. As you can see, the gear here is prevented from slipping because there's this thread on this tuner here. And so we can set the tension to anything that we want. One of the first things we have to do here is determine what is the string's linear mass density. So each of these strings is the same thickness, same gauge. These are all 0.013 gauge strings. These strings were produced by D'Addario. They're acoustic steel strings. It's the Phosphor Bronze series. I personally often play with this set, the medium string, which is 13 to 56. However, I didn't realize there was a heavier version. I'd actually prefer the heavier version, so I'm going to order those next. I tune every string down to half steps. Just because I have kind of a low singing voice. But anyway, yeah, let's check these out. I'd like to see the string gauge guide and string tension chart. That would be interesting. So I'm using the PL013 right now for this experiment. It is 0.013 inches in diameter. That's what the 0.013 refers to. It says here that the tension on it, when you have it tuned to an E, should be 27.42 pounds. That should vary though, depending on the length of the vibrating string. Guitars are different as far as open string length, but okay, around 27.42 pounds. Okay, so here I have a set of acoustic guitar strings. This is a E string, and what I want to do is get its mass and its length. So I'll weigh it and I'll also measure it. So the string's mass is 0.0008 kilograms. And the string length turned out to be 1.000 meters. So I'll now use the linear mass density formula to find out what mu is. Mu is the linear mass density. It's going to be 0.0008 kilograms per meter. Okay, now it says raise the tension on a string to the point where a note can clearly be heard. We can use a tone generator or an online piano app to figure out what note we're at currently. So I'll search for a piano emulator. This first one that comes up, Apronos, is a good one because this app gives us the note names of the different keys. It tells us not only the letter of the note, but also the octave of it too. Yeah, so I'm now just going to try to match up the sound on my board here with the piano sound. Here's my sound. That's quite close. Alright, so my note is just about a C sharp. I can tell that my instrument is actually just a little sharp, meaning its frequency is a little bit higher than the C sharp on the piano right now. So I'm going to take this little bridge here. It's just a wooden dowel. I'm going to wedge it underneath the strings so that I can more easily measure the effective vibrating string length here. Right now it's just based on where the string leaves the post there. And at the other end, what I have is I have the strings fed through these little metal tubes. But I don't want to just rely on that for the experiment. I'd rather just wedge this underneath so that I can measure more effectively. Yeah, so let's do that now. Just sliding the bridge underneath the strings. Now I'll just roll it until it gets to the end. Okay, so something like that should be pretty good. And now just put another bridge at the other end here so that we can measure very rigorously. Okay, so that looks pretty good there. The instrument is ready to be tuned now. So let's see what note it's at currently. Looks like an E flat. My strings are a little sharp compared to that, so I could just roll the pin and make them a little longer. That'll fix the issue. It's pretty good right there. So that sounds pretty good. I also like to pull on the strings manually and just physically see if they'll go a little flat just from pulling. Then you can tighten them back up, and then there'll be less chance of them loosening on their own after that. Let's see if any of them went a little flat. A little bit. Okay, it sounds pretty good. We're at an E flat, so we should calculate what that frequency is. In the app, they tell us that the key I was pressing was E flat 4. And that sounds pretty much like the tone that I'm getting from the string. However, it is highly possible that I could be mistaken too. And there's other E flats on the piano, such as here E flat 5, which also sounds quite a bit like the note that my instrument is making. There's also an E flat 3, which has a similar tone as well. It's my view that I think what I have right now is actually E flat 4. I feel like that note sounds most similar to what I'm playing. However, if there's ever any doubt, we can just go to the Audacity software and do a recording of the instrument. So let's go ahead and make a quick recording. Okay, let's record the instrument. Yeah, so all those three tones should be pretty similar in frequency. Let's check out the first one here. I'll just do the FFT method. Okay, so this is showing a peak, a very strong peak at 313 Hertz. It says D sharp 4 in parentheses, so that would be the same as what's called E flat. We also see that the next harmonic is at double that frequency, which is, so the first harmonic would be 2 times the fundamental frequency. So 628 is about double of 313. The next harmonic that should occur should be 3 times the fundamental. We get 937, and that is about 3 times as large as 313. So I think it's quite clear here that 313 Hertz or E flat 4 is the true fundamental here. Now we can check the other strings as well and see what kind of results they get, but I suspect it's going to be quite similar to this. Okay, we have a peak at 312 for one of the other strings. And a strong peak at 312 for the third string. So that's pretty conclusive there. Next, we're asked to calculate the tension in the string using a formula for tension. Here, the T doesn't stand for period. It stands for a force of tension. So this is the formula for tension in a string. It's going to be T equals 4 times our linear mass density, which we said earlier was 0.0008 kilograms per meter. L is going to be the length. Now this length does not refer to the length of the string that I had measured earlier. That was a string that I just took out of the package, and I wanted to find the linear mass density by figuring out how much it weighed in grams. His mass was 0.0008 kilograms, and its length was 1.000 meters. That's not the length that it's referring to here in this problem, though. The length that it's talking about is going to be the length of the string when it's attached to the instrument, like what length of string is allowed to vibrate freely. So for that, I'm going to have to measure the instrument itself. Okay, so yeah, so we just want to measure it like that from this point here where the string is first allowed to vibrate. That's called a node there, where the string is not free to move. Here in the middle, the thing is free to move. I made sure of that because I suspended it so that the string is not touching the board from one bridge to the other. So we just want that length. The length between the two bridges is what we want. Okay, so it looks like 52.80 centimeters. Now that's 52.80 centimeters, but we do want to convert this to meters. Why? Because I have meters here, and also the standard unit for lengths in physics is meters. So let's just go ahead and move the decimal back 2 places, and this is going to be 0.5280 meters. Now for frequency, we measured 313 hertz. And let's go ahead and calculate all that. So I get 87.4. The units here would be newtons. It's the standard unit for force in physics. And if we do a little conversion, we could convert newtons to pounds. The manufacturer had said that the E string, when it's fully tuned, would have 27 pounds on it. Now, of course, I don't necessarily have to have a lot of tension on this string in order to do the experiment. It was pretty arbitrary, the tension that I had put on it. But let's see what that conversion is for newtons to pounds. So it says here that you could convert newtons to pounds with the conversion of 0.225 pounds is equivalent to a newton. So on the side, I'll just convert that. It's 19.6 pounds. So the tension that I have on this instrument is substantially less than it would be on a real guitar. But that's fine for our purposes. Okay, so now at this point, what we want to do is we want to find ratios of frequencies that sound good to the human ear. This is something that could be very subjective. And even if you don't know why biologically this kind of activity arouses pleasure in a human mind, you don't have to know why we feel the way we do in order to document how we feel. And so that's what I'm going to do here is I'm going to experiment with different ratios of strings to see which ones I prefer personally. And I have these little frets that I can place at different points under the string in order to change the string lengths. First of all, I'll start with the strings being equal. I think there is some value to that. Being able to strike two strings and have them be at about the same frequency, it just feels kind of cool to be able to do that. There's a certain, I guess, satisfaction you get. And what I want to do with this project is I want to say how much I like the combination. So I'm going to rate my preference of the combinations of notes. So let's say if I really like a combination, I'm going to rate that a 10 out of 10. The scale that I'm proposing of 0 to 10 is somewhat arbitrary. 10 being something that I like a lot, but I'm also not going to rate string combinations that sound bad to me. I suppose if I really wanted to, I could come up with like a negative rating for something that sounds like the most dissonant thing I've ever heard, where I just really don't like the sound of it and would rather never hear it again. I don't think I'm going to do a negative rating this time, though. I'm just going to rate ones that I think have some value, and I'll rate them from 0 to 10. 0 meaning I'm just kind of neutral on it. I don't really care whether I hear it or not. Whereas 10 would be like I really like that and want to hear that again. So I'll just start off with the ratio of 1 to 1, the original length being 52.8, and the second string length being the same. The frequency of the first string is 313 hertz. And I'm just going to put my units up here to save space and time. And the second string is at that same frequency, so they're in what we would call unison. We can now divide the lengths. It says divide L1 by L2. So we're going to do 0.528 over 0.528. And that's, of course, just 1. If we divide now frequency 2 by frequency 1, that's another way to get the ratio. This will be a ratio of the frequencies, and obviously that is going to be a 1 as well. Now, how much do I like the combination of them? I think it's pretty cool to hear two strings in unison, but I will say that my evaluation of how cool it is has a lot to do with me recognizing that there are two different strings and thinking in my head about how they could be different frequencies. But it's pretty cool that even though they could be off of each other, they're not. And I feel like if I was to just hear the two of them together without realizing that they were two distinct strings, I might not even know that two strings are being struck there. So I'm not going to put it as like the highest on my rating. And like I said, this is a subjective exercise. I'm just going to say, maybe like a 5 out of 10. I like it, but maybe there are other things I might like more. Okay, so what I'm going to do next is I'm going to put a fret underneath a string here. And I'll use the middle string as the open string. And I just want to move the fret around. until I find another combination that I like. Now, I don't have to do every single combination of lengths. There would be an infinite number of different possibilities. That's just too much to analyze. I'm just going to move the thing around until I hear another combination that I like. The combination there is pretty dissonant. I'm not really getting anything I like in that range, you know? And I'm not saying that dissonance doesn't have value. I think it can. But I'm looking for something that really jumps out at me as something that makes me feel something good, you know? It's kind of an interesting one. That's something I kind of like right there. There were a lot of similar tones in this region. But something about this has a nice tone. So I'm going to measure that length off. And let's see what ratio we're at here. Okay, 45.3. The original length is going to stay the same every time. It's really only the second string length that I'm varying. So I say 0.453 was an interesting tone to me. The original frequency would be 313. And now I need to know what the new frequency is. So I can use Audacity here. We want to be pretty rigorous about this. And let's record it now. All right, this was the note. Let's get the spectrum. So there's a very strong peak here at 723. It says it's about an F sharp. I don't expect it to be exactly an F sharp, but it might be. Now 723 is actually the first harmonic above the fundamental. The fundamental is probably something closer to what we started with, which was 313. It could be this here, the 357 perhaps. But because this peak is so strong at 723, I'm going to go ahead and just divide that 723 by 2. So 361.5, I'll round it to 362. That is apparently where the fundamental must be. Yeah, 362. There's a little peak there. Wasn't a great sample, I guess, but that works. So 362. When we divide the lengths, we want to divide the longer string by the shorter string. So we get a ratio that's bigger than 1 here. Okay, we're getting 1.166. Now I'm going to divide the new frequency, the higher frequency, by the lower frequency, the original length. And let's see what that comes out to. 1.157. Now, how much do I like the combination? I think it's a little more interesting than the last combination. I'd put it at a 6, perhaps. I could imagine there's other combinations I like more, perhaps. Maybe a 6 or a 7, I don't know. Alright, let's try some more now. That sounds interesting to me. Now, you have to keep in mind, I'm highly biased doing this because I've listened to a lot of Western music in my life. That's an understatement. I get 43.8 centimeters. But my point is, I wouldn't be surprised if I pick out notes that are part of the Western scale just out of bias, basically. But this is a subjective exercise that's expected. It's a statistical investigation. It doesn't have to be unbiased. In fact, it can't be unbiased. I'll record the note that I like here. It is a little different from the previous one. Let's look at the FFT. Okay, so with this sample, I'm actually getting a very strong fundamental peak at 382, which the Audacity system says is approximately a G in the Western scale. So 382 hertz. Let's write that down. And we'll divide. I get 1.205. And it looks like 1.220. Now, how much do I like the combination? I think I liked it a little more than the previous one. All right, let's keep going. So that's where I was at. That I don't like. I don't like that. It's getting a little better. Not terrible, but not quite. That's too far. I went too far. Gotta go back. That's too flat. It's pretty good right there. It's almost like, depends how bright you want to make it, right? Exactly where you put it affects the brightness. I think that has a really nice sound. Yeah, I think right there. Okay, let's measure 42.4. And let's record it. They do sound different. And it would be kind of interesting to take one of these samples, maybe make a new track. Be kind of interesting to pair them up. These are the notes that I liked. Let's see what frequency this one is. Let's see. Maybe I should not get the beginning of the note. Because I don't want a lot of the transients that occur when you're just striking the note for the first time. I really want to focus on what's resonating here, so I'll just focus on that part. There's a strong peak at 393, 394, $1.245. $1.259. Now, how much do I like that combination? I liked it quite a bit. I would say an 8 or a 9. I like how it gave me a very peaceful feeling. Yeah, there was a little bit of a gritty distortion almost character to it. How the strings were close together, so they sounded a little bit dissonant, but not in a bad way, if that makes sense. Let's try some more. That's a little dissonant. Yeah, that right there I like. $39.9 centimeters. Yeah, that was a nice sound. Strong peak at 417 hertz. And that's a really beautiful harmonic series there. So this is obviously the first harmonic above the fundamental. That was a little low in volume, at least in this analysis. But the other ones, it's quite a beautiful series how they decay in volume as you go higher in frequency. Okay, so 414 hertz, maybe 417. I could average the two, say 415 hertz. Yeah, so this one I liked quite a bit as well. Perhaps an 8 or a 9. It was very clean, not much dissonance at all. And I'm not really rating them in multiple different categories or multiple different dimensions, such as how they make me feel, like how clean do they sound, how dissonant do they sound, how bright or how dark. I'm not going that far with it, but I'm just saying that this was a combination of note to me. I thought it had something interesting to offer to the analysis. That I don't like. It's starting to sound like a Halloween film. It's dissonant. Harsh. Getting better. Too far. And yeah, that's pretty clean as well. Similar to the last one. 35.4 centimeters. Let's hear the combination together. That's a nice harmonic series. 471 hertz. Okay. This one was also an 8 for me. Maybe a 9. Maybe I like it just a little bit better. That's not bad. Yeah, let's try that. 33.6. $497 Hz, 498. Beautiful harmonic series there. I'd say I like this one either like a 6 or a 7. It was a solid combination, but I don't think I like it as much as some of the others. And so there are a lot of others that I find interesting in this region. Like that one. But I think I'm going to skip ahead. It's very dissonant there. But that's an interesting one right there. So these, they sound like the same note. However, one's got a lot higher pitch than the other. But I'd say they're the most closely related two strings that we've seen thus far since the two that were in unison, at least. So let's definitely record that one. 26.6. Yeah, let's hear those two together again. They're so similar. So we've got a tone of 629 or 628. Okay, and I like those two together quite a bit. Maybe I'll put a 9 or something. Now there are many, many more ratios that I could investigate, but I'll stop there. And now I want to put them into a Microsoft Excel graph. In order to do that, like it says here in the activity, we want to create a column in Excel for a lot of different frequency ratios that we might have investigated. And we just want the numbers, 1 all the way up through 2 or beyond, and we're going to count by hundredths. So I'll start with a column called frequency ratio. We'll start with the lowest ratio that we investigated, which was 1 to 1 there. Then we'll try 1.01, 1.02, 1.03, and so on. In order to keep this pattern going, you can select 2 adjacent rows here and then click in the lower right and drag. And what it's going to do is it's going to keep that pattern going as long as you want it to go. And we could go all the way up to perhaps 2. So just drag that down a little more. And there we go. We've got the numbers 1 through 2 counting by hundredths. Now, certain ones of these ratios stood out to me as ratios that I really liked. And so what I want to do next, like it says, is to go through and put your rating of the frequency ratio that you liked next to the ratio itself. So make a new column for rating, and then I'm going to look at my ratings that I had awarded here. So there was a rating of 5 that went along with the 1-to-1 ratio. Now I'm rethinking it. Now I'm thinking I want it to be higher. But let's just put a 5 next to the ratio 1 that we liked. I'll even highlight it here. The next ratio that I investigated that I liked was around 1.16 or 1.15. Let's find that one. Yeah, I'll average the two, and we could go with 1.16 being the ratio that I liked, and I rated it a 6. So all these other ratios in between, the 1 and the 1.16, I didn't like them, or I just didn't notice if they were interesting. These are really the 2 that caught my attention in that range. Next one is 1.20 or 1.22. Maybe we can average it out to 1.21, and I rated that a 7 out of 10. So that was an important one. Let's see, 1.245 with 1.259, average them two, and you get 1.25 perhaps. This I rated a 9. I also liked something around 1.32 or 1.33. I rated that an 8. I liked 1.5 as a ratio. That was a strong like. It was a 9. I thought 1.57 was interesting. I gave that a 6. And I did say that there were quite a few more that I might have liked between 1.57 and 2. But I did make special note of the ratio of 2. I gave that a 9. So what I want to do with this is I want to create a graph showing which ratios stood out to me as ratios that I liked hearing. So in order to do this, we can select the rating column. You have to click on one cell, go to the bottom, and hit Shift, and then click again. And at that point, you'll want to go up to the menu here in Excel and click Insert, and then choose this bar chart. And the first option is the one that we want. And it gives us this nice graph showing the locations of ratios that I liked. Now, right now, the horizontal axis isn't quite right. I'd like the horizontal axis to be the ratios that I liked. So in order to fix that, what we can do is hit on Mac, Control click, and go to Select Data. I'm using the Mac version of Excel right now. I realize that there are multiple versions. Seen that the other day. And they often have very different ways of getting things done. But this is just the standalone version on the Mac. So what you have to do is you have to select the axis labels that you want for the horizontal. So what you can do is just click on that field and then go to your frequency ratio column, click at the top of it, and then go all the way down to the bottom and hit shift click. That's going to select that whole column as your horizontal axis labels. So then just hit OK, and that'll fix it. So now what we have is we have the ratios that we liked listed underneath the bars. The height of the bar represents my rating of how much I liked the combination. So what I'm proposing here is that there's a mathematical reason that my ear and my mind responds to these combinations of frequencies. And so what I want to do next is I'd like to create a similar chart showing some mathematical ratios that might be important in music. So what I'll do next is come up with a new column. And I could call this something like math ratios. Now in the instructions for this activity, it says that we want to make a second graph using the decimal equivalents of these important mathematical ratios. The ratios are 2/1, 3/2, 4/3, 5/4, and so on. These ratios here fit the form of a number in the denominator and that same number plus 1 in the numerator. And these are their decimal equivalents. So what it's saying is that 2 divided by 1 is 2. 3 divided by 2 on calculator makes 1.5. And 4 divided by 3 on calculator makes 1.333. And so on. It's possible that these numbers may have significance when it comes to ratios that people like. You might even recognize, some of these numbers as being numbers that I had picked out on my own just from listening. If we match them up, I did like the ratio 2:1. I gave it a 9. Right here, see, we've got 1.985 and 2.006. They round to about 2. And I really liked that combination. If we look at 3/2, that was 1.5. I really liked that combination as well. Gave both of those a 9. Here, the ratio of 4/3 was 1.33. And I did select something around 1.33. So there is something going on here with a connection between the brain and the mathematics. For some reason, our brains are wired to like mathematically significant ratios. These mathematically significant ratios of simple, low numbers. So what I'd like to do is do exactly what I did before. I'm going to put I'm going to mark where the mathematical ratios occurred in my Excel sheet. So certainly 2 was a mathematical ratio. I'll just give it something like a 10, just saying that it appeared in the mathematical series. 2 over 1 was one of the things that appeared. I'm not going to rate them on a scale 1 to 10. But I'm just going to say that 2 and 1.5 and 1.33 are ones that I want to mark on the Excel sheet with a 10. Other numbers that appear here are 1.25, 1.2, and 1.167. Then there's some other ratios here, 8 over 7, 9 over 8, 10 over 9. So interestingly, I wasn't crazy about ratios in this region, talking about 1.08, 1.09, 1.1. These particular ratios, they would be where the fret is close to the end of the open string. And they're not bad. They might have something to offer here. I just didn't pick them out as particularly satisfying or significant. They sound a little more dissonant because strings are so close together in pitch. It's hard to pick out one that I think is particularly significant. But either way, I'll write them down on the Excel sheet. We also have 1.10, 1.09, and 1.08. So it's getting a little muddy in that region on my graph. And at that point, it's a little hard to see significance in the ratios there. But anyway, now I'm going to make a graph of those. I may be able to add them to my existing graph here, which would be kind of cool. I could make a totally separate graph of them. So let's do that first. So this is the graph that I get. Let me bring this guy up and look at him compared to the graph that I had generated myself. I'm going to go to the axis labels. And let's make sure that we have the ratios selected. It looks like right now Excel it's starting my data at H16, which is here. I don't really want that. I want to include all the way up through H8. So I'm just going to manually change that. It kind of just did that automatically. But yeah, I want it to, I want my graph to start at 1. Even though here I didn't put any bars, I'd like to be able to match up my graph with the mathematical ratio graph, so we can see how similar or different they are. And that looks pretty good. However, like I was saying, it would be really interesting if I could get them both to be on the same axes. Let me click select data on my original chart. See if we can add a new series. Yeah, so series 2, I have to go to the Y values here and just select the math ratios. And there we go, that looks pretty neat. So what we see here is there is some kind of correlation or association between what I liked and the numbers of the math ratios. So it's not a coincidence that I liked the ratio of 2, and 2 was also one of these mathematical ratios. And also, it's not a coincidence that I liked 1.5, and that was one of the numbers on the list as well. With some of these here, there's a little bit of discrepancy where seems like maybe they don't line up perfectly, but that could also be due to a little bit of experimental error. But there does appear to be a correlation between what I liked and the math ratios. So I did this activity with an entire class recently, and I asked all the students in the class to share their data so that we would have not just one person's preferences, but many people's preferences. And so I'm going to now add the class data to a chart. And what we'll see there is that there's going to be a whole aggregate of people and their preferences. And I'll bet that if we combine all the preferences of a wide range of people, I'll bet that people are going to still tend to like ratios that are mathematical. So let's get that data. So I'll make a column for the whole class. And I'll try to add some data from the class. Now this is aggregate data, so I'm just adding everybody's results together. Okay, so I added some data from the class from frequency of 1 up to a frequency of 2. And they actually had selected some ratios that went well beyond 2. I didn't tell them that it had to be a ratio from 1 to 2. They just had picked ratios that were quite large in many cases. They were placing their frets beyond the halfway point. Probably, way up here in some cases. They were getting ratios where you had an open string with something that was like a lot higher pitched. And that could be okay, So let's see what they had selected. Okay, so that's all the data. I'm now going to make a chart out of it. Okay, so this was the chart that the class had come up with. Now this chart that the class created goes well beyond the ratio of 2. Let's get the horizontal axes correct here. So let's select the frequency ratio column. I'll go all the way down to the end of it. I had to go all the way to beyond 5 in order to get all the class data in here. And so they had an interest in ratios that were quite large in some cases. So if I really want to line, their graph up to mine, I really have to expand theirs quite a bit. Let's see, so the 2 occurs right here, so I still have quite a ways to go if I want it to be to scale with my graph. Gotta go a little farther. Okay, so that's pretty good. Now keep in mind, this is the class's data, which includes a variety of students. Some of them may have musical background, some may not. And it's kind of interesting if they don't have a musical background, because you'd think that in that case they would be a little bit less biased when they're doing this activity. In my case, I have a musical background and a math background, so I somewhat expect myself to be quite biased in this investigation. I'm trying to do it without, I guess, searching for those mathematical ratios and those equal tempered scale ratios that I've heard so many times in music, right? But even if people don't have a music performance background, they've certainly heard Western equal tempered scale music. And so we're all a little biased in this investigation. Now, some of the things on the class graph are surprising to me. To be honest, this is my first time doing this particular activity. I'm surprised that there's not more agreement with 1.5 being a desirable ratio. That's one of those low ratios, 3/2. Most people like that combination of notes. I do see, however, that they did select 1.33, and that's a similar mathematical combination of notes. That's 4/3. I'm surprised a little bit that nobody picked the ratio of 2-1. That is a little surprising. That's an octave. I would have thought that more people would zero in on that one. But with statistics, you never know what you're going to get. A lot of people chose the 1-to-1 ratio, the open string. Okay. I see there's quite a bit around 1.2, which is a minor third. There's quite a bit around 1.25, which is a major third. And then, like I said, the 4/3, which is a perfect fourth. But I'm surprised that perfect fifth wasn't part of their analysis. Now, there's a whole bunch of data here that goes beyond the ratio of 2. Now, the fact is that these notes are going to be, in a sense, duplicates of what we see here. I started my investigation out with an E flat being here, and so there should also be an E flat at the ratio of 2. Then the cycle starts all over again. Yeah, so I see here they picked a ratio of 2.5. Now that should be a major third, actually. And I see that they picked 3, so 3 times the frequency. So that would be a perfect fifth right there. So even though they didn't pick the ratio of 1.5, somebody at least did pick a ratio of double that, which is really a perfect fifth, but it's an octave above. Let's see. 3.5, I guess this would be, if we cut that in half, the ratio that corresponds to it that's between 1 and 2 would be 1.75 or so. And then they picked a ratio of 5-1. 5 times the frequency. Well, 4 times the frequency would be 2 octaves, right? So this is a little bit above 2 octaves. Okay, interesting. So how can we go through and find the notes that correspond to these markings? So we could make a new column here, and maybe I'll put it just to the left of the ratio column. Let's make this a musical note column. So I started with E flat, right? But even if I started with some other tone, all these same ratios would still be valid. These ratios would be valid for any starting tone. So let's just say hypothetically, if we had started off with a C, like let's say C4, for example, what notes would go next to these ratios? So anytime you double a frequency, for example, if I go to a tone generator, I'll use this one, this Giessen. I like this one. The tone for C4, let's look up what it is. C4 has a frequency of 262 hertz. And that's what it sounds like. It matches with the online piano. So an octave above that should be double that frequency. Let's try 524. It matches. If we double it again, we should be able to get the next C above that. So that would be 1048. It matches. So in my Excel, if C4 was designated as a ratio of 1, then that means that a ratio of 2 would be C5. But the next ratio of C would not be 3. Okay, because if we take that 262 and multiply it by 3, we would get 786. But 786 is not a C. It's a G. So that's a perfect fifth. So this would be a G. And the next C would happen at 4, which would be the 1048. So what is 5 times the frequency of C? $1310. It sounds like an E. Now that E is actually an octave above E5. It would be E6. So a C and an E, that's actually a major third that they liked. In the Western scale, a ratio of 1.16 would be designated as approximately D. 1.2 would be an E flat. 1.25 would be an E. 1.33 is an F. A G is 1.5. 1.66 is actually an A. So the equal tempered scale is a 12-note scale, and it didn't have to be 12 notes, but that number has been decided upon because a lot of the ratios and frequencies that you get with that happen to correspond to mathematical ratios. It is not a perfect scale. There is imperfection, but I believe that over the years it's been decided upon that the complexity and the level of interest that these notes provides to music outweighs the imperfections that get introduced. Let's look at how the equal tempered scale works. What you do is you start with a particular frequency, such as the frequency that I began this investigation with. I started with an E flat. It was a frequency of 313 hertz. And now we're going to see how to find subsequent frequencies in the equal tempered scale. First, let's get a picture of the piano. Okay, so here's a picture of the 88 key keyboard. The note that I started with personally in this investigation was E flat 4. That is this key here. It is a black key on the piano, and that was my start. That is a ratio of 1. And what I want to do is find the frequencies of the notes that are above that. The way you find it is you start with your fundamental frequency of the E flat, which was 313 hertz. And then in order to find the frequency of the next note, which would be E4, you have to multiply. So what do we multiply? We start with E flat 4 and we multiply it by 2 to the 1 over 12. Because there are 12 notes in the equal tempered scale, this is going to take us to a new frequency, which is going to give us the frequency of what we call E4. So let's see what that is. It's going to be 313 hertz times 2 to the 1/12. So on calculator, we'd write that like this. It's 332 hertz approximately. And let's see what ratio that makes. We'll divide the 332 by the original 313. It makes a ratio of 1.059, an important number in the equal tempered scale. That is approximately 2 to the 1/12. And so that's going to be the next note. And the first one was E flat 4 that we started with, and now we are at what is called E4. My original string length was 0.528. And in order to get the new string length, what I should do is actually take that 0.528, and what we can do is divide by 2 to the 1/12. Because we're going to need a shorter string to get a higher note. 1.498 is the length that it would need to be. And 1.059 is actually a ratio of 13/12. An important ratio in the equal tempered scale. Because what the equal tempered scale will do is it makes every successive note 13/12 of the frequency of the previous note. Now, in order to get the next frequency, what we could do is we can multiply the 332 hertz times 2 to the 1/12 as well. And let's see what that gives us. $351.3. And that would be called an F4. It is this note on the keyboard. So if we take the 351 and divide by the previous note of 332, let's see what we would get there as a ratio. .057. Now there's differences because of rounding, but it's supposed to be that the frequency of F4 is 13/12 times the frequency of E4. And that's why it's called equal tempered scale, because every note is going to be 13/12 times the previous note.